Okay. So for next Monday, you should try these 3 problems. So the first one is on the Lagrange multipliers. And these 2 are about the motion in a central force that we are going to discuss today on Friday. So wait for the weekend before you try to solve those 2. And then I have a 4th problem that is not this nice feature that problems for which the potential only depends on the relative distance between your bodies, so central forces. And then if you look at the 2-body problem, that can be reduced in a systematic manner to a 1-body problem, you remember, in which you have, sorry, in which the Lagrangian then becomes, so 2 bodies, one of mass m1, one of mass m2. Then if you write a big capital R, the position of the center of the mass of the system of the 2 bodies, the Lagrangian has a term that is just the kinetic energy as if all the mass of the system has been concentrated at its center of mass, plus a term with this reduced mass that is defined as the sum of the reciprocal quantities, 1 over mu, 1 over plus m1 plus 1 over m2. And the velocity is taken, so I have 2 points, 1 and 2, and this is R, and then somewhere is the center of the mass, and this is big R, okay? And then, because it's a central force problem, you have your potential that we haven't specified yet. This will be the next step. But we know that it's a central force. Therefore, the potential can only depend on the relative distance, little r. Okay. So that was where we stop on Monday. No, last week. So now I want to, maybe I should remind you that clearly there is no explicit dependence of capital R, and therefore, one more time, I know that there is a conserved quantity, right? That is the conjugate, the momentum that is conjugate to the missing cyclic coordinate, and this is clearly the momentum of the system as a whole, right? Because the force is only, in a way, an internal force, right? Because it acts on the 2 components. And therefore, the system as a whole has the momentum in space conserved. Okay, so it may move with constant speed, and if that is the case, it will keep moving with constant speed, or it is at rest, maybe with respect to some frame of reference. I don't care. That we already said. I mean, this is in fact the case. If you look at the system Sun, Earth, the center of the mass is somewhere close to the Sun, and we don't really care. I mean, you know that the system, our solar system, is moving very fast toward the Virgo. I think some cluster is very far away, is moving very fast in that direction. It has been moving this way roughly with constant speed, and okay, it doesn't matter, right? Because this is true as seen from an observer that who is at rest with respect to our galaxy and the Virgo cluster, But for us, we are not. I mean, we are riding on top of our galaxy. So for us, it is the same as if they were at rest, the center of a mass. Okay. Actually, it's even more complicated. You understand? I mean, because we are in the solar system. The solar system is moving within the galaxy, and the galaxy, our galaxy itself, is moving in that direction, in another direction. And then the cluster of galaxies to which we belong itself is moving in some other direction that I don't know. But the nice thing is that as long as they move with constant speed, it doesn't really matter. This is what Galilei taught us. Well, not us, but whoever was around at the time, that physics is invariant under those transformations. Now, next year, when I will be teaching you electrodynamics, we will see that, well, probably you already know that this is not completely true, because physics is not invariant under the Galilean transformations, is invariant under Einstein, right, a relativistic transformation. But as I said already, as long as the velocities are small compared to the velocity of light, this Galilean invariance of inertial systems is a very good approximation. And that's also the reason why we can, well, we don't have a laboratory class here. That's a pity. I mean, so we cannot do experiments, but all experiments you can try at home or here with a very good approximation. The solution, what you see is what you would see if you were at rest, right? You don't see any acceleration around because the Earth is rotating. As I already said, I mean, in fact, you need some very specific effects, and we will study those when we talk about the rigid body. There are ways to see that we actually are we are rotating. You know that, right? Do you know how do we know that? I mean, okay, the sun goes around, but it could be the other way around, right? As people thought at the beginning. I mean, we could be at rest and the sun moves around. So how do we know that, in fact, it is us rotating? I mean, everybody knows that is the latter. I mean, it's not the first case. But how would you, I mean, you know, there are these, some people don't believe. I mean, they think that the Earth is flat and the sun goes around. So how do you convince these people that, in fact, that's not the case? I mean, the fact that the Earth is not flat is rather simple, no? Because you stare far away and you see that something on the sea, you know, disappears slowly, beginning with the lowest part. If you look at some sailing ship, right? So that's pretty convincing, at least for me. There is some curvature and the thing is disappearing. So probably the Earth is not flat. But to convince somebody that, in fact, we are rotating, you need some something more. So you don't. So why do you believe that the sun is at rest and we are going around? We are rotating. Because they told you, or not. But you should always, you know, you shouldn't take nobody's word for, I mean, you should check. Okay, we will come to that later on. So now that we have reduced the two-body problem to the much simpler one-body problem, you see, it's just one. Now I look only at this part of my Lagrangian. This I forget about. It's just the center of mass that moves with some constant velocity in some direction. Okay. Good. But now, for me, the Lagrangian is just this, and you see, is a one-body problem. It's just that I have this funny-looking mass that, however, is just you know, once I give you the two masses of the two bodies, then I can compute this reduced mass. I plug in here, and I have a one-body problem. Okay, very good.
instance, when you put water on something and then like a sinker,
Right.
some kind
That's Newton argument, right?
okay.
But how would you do that for us here on the Earth? I mean, that shows that the vessel is rotating, right? Did you understand what he's saying? If you have a bucket full of water, right? If you sort of spin in this way, you see that the surface of the bucket, right, it doesn't stay flat. It goes like this because you have a force pulling away, the centrifugal force, right?
In the
But
same direction, always.
right. But how would you apply that for us on the Earth? We don't see the sea going like this, right? It is not the tides, you know, the tidal motions. Okay, think about it. We will discuss that. I mean, this was a big issue at a certain point. People really thought hard. For instance, Newton, I mean, this is an argument for the absolute frame of reference. You know, Newton argued that you can establish this way. Okay. So now let's just look at this term here. Let's, in fact, erase this. That we don't. That's all we need. And in fact, I even don't need this sketch any longer because now I really want to think of a single body with the reduced mass moving under the effect of this potential. And so it's a body there. If I'm sitting somewhere at so the picture now is, here is the origin for this vector r, and I have a reduced mass body here moving in some way, and I have a force pointing toward this point, right, given by the gradient of that potential. Okay, so this is the central force problem. Also, maybe I should, if you take the system Earth, Sun, you see that if you have a very, right, you see what happened, that if you have two masses, the size of which are very different, then one of the two dominates, right? Because if you put here a very large mass and here a very light one, right, this mu goes like m1 times m2 divided by the sum, right? And then you see that if one is very heavy, then you know, you can neglect this one. So now assume that m1 is much smaller than m2. Then you can neglect this with respect to this. Then these two simplify, and you only have the light mass entering the equation. So if I'm thinking of our planet with respect to the sun, the light guy, it's us. And so here I can put the mass of the Earth with a very good approximation. There are corrections, but there's more. So it's just one vector, okay? And what is the symmetry of this problem? I think now we go hunting for conserved quantities, right? Time, yes, very good. There is no explicit dependence on time. So I expect the energy of the system to be conserved, but also, you see, it only depends on R, right? So you do expect a spherical symmetry, right? Don't you? You see, there is no explicit dependence on angles, or it's just R. Again, because I'm assuming that it's a central force, right? If it had, actually, I mean, I should put something like this to be more precise. It only depends on the distance, not if it's here or rather there. Therefore, I do expect some spherical symmetry, and therefore, what spherical symmetry tells me that I have a conserved quantity that is the angular momentum, right? That usually is defined as R cross P, where P is the momentum of this guy. You know this, this symbol, right? So it's a cross product of two vectors. That there are two ways to multiply vectors, as you know. One produces a scalar, and one produces another vector, and this is the latter. I mean, you take two vectors and you produce a new vector. And you know how there is this rule that they are all sort of orthogonal to each other. If you have two vectors, they identify a plane, and then this is sticking out from that plane. Okay, this is going to be important. So in other words, you see that because, so this I say is conserved, right, because of the spherical symmetry. So I have two conserved quantities, at least, the energy and the angular momentum. They are really four, right, because you should look at the component. So the angular momentum is conserved in three directions. And because of this, you see that because of the definition of vector product, this implies that the little r, right, is always orthogonal to big L, right? Because by definition, if R and P, say, are two vectors in the plane of the blackboard, and if you have two vectors, you can always identify this plane, right? And then I guess it's the right hand is like this, so actually it's pointing that way, right? You agree? Okay. And you see, anyway, it's pointing inside the blackboard. Therefore, it's orthogonal to R. And also that means that the motion of this particle, because of this property, is always in a plane. That's very interesting. Because of the nature of this force, if you have this particle moving, it's not going to move like this. It's always moving in an orbit that stays in a plane. In other words, you can always define a plane in which your orbit is going to stay. And it's going to stay there. For instance, again, let's take our favorite system, that is the solar system. The sun and the earth moves, but it moves in a way, or if you want, the sun is moving, whatever you prefer, but it's always moving in a plane, okay? It's not, I mean, it's not doing something like this to a very good approximation. That's a huge simplification, you understand, because from a three-dimensional problem, we are, we are moving toward a two-dimensional problem, okay? In fact, it just what is that? It just happens that almost all planets are very close to the same plane, right? So they could be, they could be all askew, because this is only telling you that for each of them you can identify a plane, and then it moves in that plane. But as a matter of fact, because of the initial conditions and the dissipation that you have in the system, really we are almost all in the plane, this ecliptic plane. So that Mars, Venus, Jupiter, Saturn, they are very close to all moving in a plane, and that plane is to a very good approximation the same. That's why when you see pictures of our system, you see all the planets aligned in a way. That's not obvious at all. I mean, why Mars is not going like this and the Earth like that? From this, they could do it. The point is that they interact. I mean, there are high order effects, because clearly it's not a two-body problem once you put in all the, well, how many are there? 8 or 9 planets that we have. So they tend to dissipate if they are not in the same plane. And so that's what the final situation looks like, I think. I'm not sure, actually, about this. But for us, this is a huge simplification. So I said we have 4 conserved quantity. Now I'm going to spend one of them, that is this, and I reduce my degrees of freedom from 3, okay, to 2. Okay, so I spend one by using this conservation to assume that the motion is taking place in a plane. So in fact, how many coordinates do I need? This is, in principle, I have a three polar coordinates, right? It's a spherical problem, three polar coordinates. Usually, well, let's agree on the names of these things. They have historical names. Well, one, of course, is this modulus of the r. So this is the obvious, the radial distance. And then, given the radial distance, all you need is the same number of coordinates that you need in order to identify a star, for instance. Now, if you go on the internet, I guess now, in the old days, there were books in which you had the position of all stars every day in the year. Well, obviously, they wouldn't give you the R because that doesn't matter. You're just standing here and looking. All you need are two angles, right? You need to be told in which direction to look for the star, or for the sun, or for the moon, for that matter, right? And then how, or what height you should look to see it, right? So you see, you need two angles, this angle, and this angle is called the, I guess so let me call it theta and psi. And so this angle in the plane, I call it the azimuth angle. And the other one is the zenith angle. I guess because the zenith is the direction right above. But you understand that true in spherical coordinates, I need three coordinates. But because I'm spending this 1 out of 4 conserved quantity, I can get rid of one of these. And usually you get rid of this one. I fix it to be pi over 2. And that is good because this way this angle is fixed, is the zenith. So it is perpendicular, the direction perpendicular to the plane in which the motion is taking place. Okay, so this is fixed. I don't have to worry about that, and because, as I said, the motion is taking place in a plane. Actually, you understand that I have used more than one. I really use two of these because if I say that something is moving in a plane, I've fixed two angular momenta here, right? And the only one left is the one in the plane, right? So really, I've spent 2 out of 4. So I'm still left with 2 first integrals, and I'm going to use them to solve the problem. Okay? Is this clear? So I'm inching my way toward solving this problem. So now I have introduced my coordinates. So since I've introduced my coordinates, I can write the Lagrangian in a more appealing way. So essentially, I'm in polar coordinates, right? Because that's what I've done. So let me erase this. So since from now on, we always mean that we are dealing with the reduced mass. Let me call the reduced mass little m, because I don't like to write mu all the time. So then the Lagrangian is the one I wrote before, except that I write m. I like it better than mu, but it is mu. And then I write the kinetic energy in polar coordinates, because I hope I convince you that this is okay, because the motion of the planet is taking place in a plane. And this, by now, I hope you know by heart how to write the kinetic energy in the polar coordinates. And then I have my potential that clearly, by definition, of central force can only depend on r, not on theta, even less on psi, the zenith angle. So now back to the conservation laws. I said that I have 4, 2 I've used. Now I can identify again that I have the energy, of course, because you see there is no t dependence. And now I can identify the one remaining component of the angular momentum that is conserved in this system, because by inspection there is no theta, explicit theta dependence. Therefore, if I take the derivative of my Lagrangian with respect to theta, right? This is clearly 0. By the Noether theorem, the derivative of my Lagrangian with respect to theta naught must vanish as well. And this quantity is conserved. And this quantity is what? Well, we already met this guy in some of the problems we discussed during the problem section or before. So I call this p theta, that is the conjugate momentum to my theta coordinate, and you see that it's just m, right? M r square theta. And so this is the remaining third component of the angular momentum that is conserved, that 2 I've used here, and 1 I'm using here. So the equation of motion for this is trivial. It's just this one. P dot theta is simply vanish, 0. So that means I can give a name to this. I already given the name here, but usually by convention, this thing is also called the angular momentum, right? That component. So it's also p theta is usually indicated as little l. So we will switch from one to the other. And so this fact that L defined m r squared theta dot is conserved, so this quantity is conserved, is the conservation of angular momentum for our system. Actually, this was observed, for instance, you know this Kepler's second law. Do you remember this? I mean, it's hard to remember because, but this is in a way, you see this quantity is close to be the areal velocity, right? You understand what? Say if you have a trajectory like this, and you have r, right? You see that this is r d theta if this is d theta, right? The infinitesimal. So if I write 1/2 r square, 1/2 r square d theta, right? This is the area that you have here, the infinitesimal area. So you see this is essentially this quantity here, right? Because if you take dt, except for a constant, that doesn't matter because everything is constant, right? So the conservation of the angular momentum for Kepler was the area swept. The area swept out by the radius along the orbit, okay, for unit of time is constant. This was called the Kepler's second law, I guess. Very important because it's a property of the orbit, and now in modern terminology, it's just a consequence of the conservation of the angular momentum. Okay, so for Kepler was this fact that the area swept in a unit time was constant, so the planet was moving in such a way that this quantity, this area remained constant. In our language, the planet moves in such a way that the angular momentum is conserved. That is somehow a more interesting way to put, but of course Kepler didn't have the Lagrangian and all. You know, we are standing on the shoulder of a much bigger man. Okay? So how far can I go without telling you what is V? So I guess this is the question. And actually I can go on because now we can do another things. We can go back to the other conserved quantity. Remember that we had the energy and then the angular momentum. Now the angular momentum has been taken care. But I can also write the energy now. So this you remember. And you remember the energy is going to be well, it's essentially T plus V, right? You should write dl d theta dot minus L, and if you do that, you see that you get essentially, because you have like you switch the sign of the V, so the energy, or the Hamiltonian, as we will call it later on, is just this. Okay, do you all agree? So you see I can write this, and I can also do a little trick, because you see I can really get rid now of this constant, of this variable altogether, because I know that theta dot, whatever it is, right, multiplied by this is a constant, so I can exploit this conservation law to write theta dot to be L over m r squared, and then plug it back there. And this is very nice, because now I have that the energy is only a function of r. So I've reduced my three-dimensional problem to a one-dimensional problem. And as I already said, one-dimensional problems are nice because we really know how, we really see what's going on. So let's do that. So I have m over 2, right? Then I have r dot square. And this term here, I substitute for theta dot the square of this. So I get L square, right? Then divide by m square, but I have m over 2, right? So I can just keep 1m, and then r to the fourth, but then I have r square, so I just have r square. So essentially I have this kinetic term, then this, and then whatever plus, because it's the energy is there. This is the energy of your system. And as I said, this is really a one-dimensional, 1D problem now, because I only have one trajectory that is r as a function of t. Okay? So clearly I cannot solve the differential equation as long as I don't say something more about v of r, but still I can have a qualitative discussion of something that helps me in understanding the solutions. Because you see, this term here, we will call it the effective potential, because you see it's the only part that depends on r. So I sort of, everything that depends on the velocity, I sort of call it the kinetic energy. And then what is left is the potential, okay? And this all quantity is conserved. Therefore, the velocity that is r dot, so I call it v, okay? V equal r dot. I guess that this is the definition. Can be rewritten if you take, you take this everything on the other side, okay? And you see that this is just the square root 2 over m, that is this term I have here. Then I took the effective potential on the other side, so I have E minus the effective potential. So the velocity at each instant time is given by this expression. And you see that because this is a square root, I mean, this quantity must always be positive, right? If this becomes negative, you get an imaginary velocity that we said is no good. I mean, in classical mechanics, all quantities are real. I mean, this is not quantum mechanics. Everything is real. So you get a sort of constraint. And now if you draw the effective potential, for instance, you see this is a very nice way to discuss in a qualitative manner a problem. You can, in a way, draw some conclusions. Let's do that. Let's take a simple example that will come out again later on. So let's take the Kepler problem. That is the problem in which the central force is Newton, universal gravitational force. This means the potential is minus some constant 1 over r, right? This, by anyway, is going to be the most relevant case. So then you see that here you can plot the effective potential, right? And on the other, so the r, and then you have well, the effective potential is made of two parts now, right? Because I have L square 2mr square minus this k over r. So I can draw the potential, actually the effective potential, but let's draw first the two terms. So how is this term? So this is the zero. So if I want to draw the Kepler potential, how is it? How does it go here? Help me out. So it's a 1 over r with a minus. So it should be here. So let's start from infinity. Given the finite size of the blackboard, infinity is here. No, there. And then it goes like what? Like this, right? So this is the minus k over r. But you see the effective potential is the sum of these two terms. So you do also have a positive term that in fact is a little sharper than 1 over r. That means it goes a little bit, so the other one goes like this, right? 1 over r squared. So this is L squared 2mr squared. And the effective potential is the combination of these two. So you can combine them together, but you see that because this is r squared, so it's a little flatter than r, right? So it starts out where this is larger. So it starts out following the 1 over r, right? But at a certain point, this guy starts becoming bigger. When r is smaller than 1 and becoming closer to 0, now this one goes to infinity, to plus infinity faster than this guy goes to minus. So the potential is going to be something. It goes down, then it remembers that there was the other term, and so eventually it goes like that. So this is the effective potential. So the angular momentum is acting as a sort of effective potential, a correction to the effective potential, right? Because you see that if you start out with 0 angular momentum, that is the case if you drop from here to the sun with 0 angular momentum, with 0 velocity, except in the radial direction, then you would see only this potential, right? But because in general, for arbitrary initial conditions, you do not follow this trajectory, you always have some component of your velocity away from the radial distance, you see an effective potential. You move as if the potential had been this one. In fact, this is what you have. And therefore, the potential is dramatically different because instead of going to minus infinity here, actually goes to plus infinity. And you understand that this is as, for instance, can you reach the sun? Can you reach the sun at all? Right. So, but you cannot beat this, right? Because it goes to infinity. So unless you have zero angular momentum, there is no way that starting from here, you can fall on the sun. Because you see, you have an infinite barrier here. That's highly non-trivial. I mean, people think that, you know, if they are on a spaceship and they are kicked out, then they will fall on the sun. And that's it. You know, they burn to hell. Actually, it's very difficult. You need the special conditions to hit the things. And in fact, this is a way that we can start. I'm sorry.
Yes, but like you have just mentioned when we are starting, that normally things in classical are real. So if it is real and the thing is there, why is
this is all real.
Yes, but that thing of no one can land to the sun, I think they should be landing there.
No.
If
You
it's
see.
there, they should be finding.
No, you enter an orbit and you go around. In fact, your fate is even more horrible than because if you have zero angular momentum, okay, you go to hell, but in a reasonable amount of time. In the other case, you see, you don't hit the sun, you start orbiting around the sun. You see here, okay, I'm drawing just R, and you don't see the other coordinate, because I'm translating the problem in a one-dimensional problem. But you must think that for each of these R, you have the theta coordinate. So let me finish it, it will become clearer. So this is the effective potential that you have, right? And now you still have to give me the energy, that is the other quantity that is conserved. And so the energy is somewhere here, right? Let's start with the energy that is this value, E. As I said, because V is this E minus V effective, that's the reason why you start out with this energy at R to infinitely away, then you come closer to the sun, and then here you have to stop, because if you go here, you get an imaginary velocity, right? Because you see, here the V effective is larger than E, this is less than 0, and the square root of a negative number is imaginary. So if your energy is this one, what happened to you is that you come close. This is the closest point of approach. Let's call it R0, and then you fly away. Now we know of many bodies behaving this way. These are the comets, usually. A comet starts out with the energy that is large enough, comes in from very far away, here's the sun, right? Reaches a point of closest approach, this R0, and then it flies away somewhere. Not all comets. Some comets are on close orbits, simply that are very eccentric, so that they come back after 100 years. But most comets are of this kind here. We just see them once, and then they fly away some to, I don't know where. And so this is this motion. It comes close, and then it goes back in the R coordinate. If I plug back the full system, right, with R this distance and the theta, this angle here, then you see the full trajectory, okay? But the crucial information is already in the one-dimensional diagram. You only need the other coordinate to visualize what actually is taking place, okay? So it moves in the plane, it comes close to the sun, then because of this rule that the V must be real, when it hits this point at which the effective potential, mainly because of the angular momentum, becomes larger than the energy, is forced to come back. So you see, it's a very nice, neat way to understand the solution even without solving anything, okay? In fact, that's the best way to understand a differential equation. You must have a feeling for the solution even without or after solving that way you really understand it. How about if you have, I mean, this is a rather large energy. So, okay, you see it's up there. What do you have a little less energy? Let's say So this is these orbits in which you don't come back are called unbounded orbits for obvious reasons. But what happens if your energy actually is down here, is negative? Yeah, it's trapped, right? It's a bounded op. You see, because it cannot actually be at infinity, because there, again, the effective potential is larger than the energy. So it cannot stay there. And it cannot stay here for the same reason. So it can only stay between these 2 points that are called RA and RB. There is no tunneling, if you think of that. If you have done that in quantum mechanics, no tunneling. So that's what this particle has to stay. And what is the orbit in this case? So this was this one. How about this one? Well, it's you see, here's the sun. Then you have 2 radii. Let's call it RA, I say, and RB, right? A and B. And the orbit, I don't know what happened to this orbit, but it must stay. So it's something like this, right? It goes around like crazy, maybe, or maybe not. It can also go like this. But this I don't know, because I haven't solved the equations. I'm always, but whatever it does, it has to do it between these two lines, these 2 circles. Okay. In fact, there is a final case that what happens if the energy is exactly, I mean, here there is a minimum somewhere, right? That's the nice thing about this effective potential. If you just look at the Kepler potential, you don't have a minimum. And this is another way of saying that you fall on the sun, no matter what. It's an attractive potential, an attractive force, and you end up there. But here there is a minimum, and if I take an energy that is exactly the one, that is exactly the value of the potential at the minimum, what happened to the velocity that I erased that was here? If the 2 are exactly equal, then the velocity, the radial velocity, is 0. That means the particle has 0 radial velocity. So that means it's a circle, right? So this solution here is exactly a circle. So the planet moves on a fixed distance from the sun, because there is 0 radial velocity, and on a circle. So we have classified in a way roughly all the possible orbits that can be unbounded or bounded. Okay, those, they go to infinity, and those that remain within bounds. And then, depending on the energy, in general, they move in a finite ring about the sun, but for a special, very special initial condition, such that the energy is exactly equal to the effective potential at the minimum. It has an even simpler motion that is a circle, so fixed radial distance from the sun, and it goes around there for infinity.
Maybe an answer for the first question.
Ah, okay, you're still...
Solar eclipse, those eclipses may tell us
eclipses? The fact that they are covered.
yeah, I mean, we have solar and then we have lunar eclipse.
Yes.
So if
Okay.
then we see only one. If we are just halfway, so the sun will rotate.
Okay, so for the solar one, I can... That's the moon coming between us and the sun, right? So that could be very well. But you say for the moon eclipses.
Yeah, by seeing those 2 eclipses, we can tell who is rotating and.
Can we? for the moon, because it's only a relative, is the fact that, you see, the problem is that we have the moon between us and the sun, right? So all you need is that the moon and the sun move, and you have the two. So, I mean, let's say we are at rest here, and then you have the moon, and then the sun. When the moon is between us and the sun, you have a solar eclipse. Sometimes it's total, sometimes it's...
We can see the solar eclipse, but we can't see the lunar eclipse, right?
No, because the lunar eclipse is when the moon is here, then we are projecting a shadow, and then. But you see, I'm at rest. The moon. Let's see, the moon goes around, and the sun goes around. If the Earth is between the sun and the moon, I have a moon eclipse. If the moon is between us and the sun, I have the other. No, I don't think. It's not kinematically, you're not going to, because kinematically it's completely equivalent. So it's not a kinematical problem, it's a dynamical problem. There is an acceleration that by the way, this is a nice coincidence that the moon, the apparent size of the moon is exactly, the moon is much smaller than the sun. But the distance of the moon with respect to the sun is such that the apparent size of the moon is exactly the sun. This was not true 10,000 years ago. It's not going to be true 10,000 years in the future because, the moon is moving a little bit. Okay, but right now you have these beautiful things so we are very lucky. And is this a coincidence? Or, this is very often in physics you have this problem. You see something remarkable, and then it could be a coincidence, or it's the effect of some dynamical principle. You understand? It's like if you have two objects with masses that are an exact ratio. I mean, is this a coincidence? It just happened to be like that? Or it is like that because there is some force and then the mass is given by this. So that's always the case. It's very important to distinguish between these two things. In this case, it's pretty clear that it's just a coincidence. I mean, we don't see any dynamical reason why the moon should be exactly at that distance and the size of the moon to be. But, you may think, no, this is the effect of some dynamical process, and so you have to think about what that is. In that case, this is a crucial clue, right? You say, this proves that there is a force such the moon has to stay there. Or it's just a coincidence, so you don't learn anything and you throw away your life trying to explain that phenomenon. But this is very common in physics. And it's very important in your training to be able to tell what is a coincidence and what is an important clue. But of course that also changes from, is the theory that tells you what is a clue and what is a coincidence, right? You know about the precessions of the orbits, right? Have you heard about this? The orbit is like this, but then there is a precession. It moves. And Mercury, that is the closest planet to the Sun, has the largest precession. It moves, right? This was known for. But from the point of view of Newtonian mechanics, this was a sort of a coincidence. It was just due to the fact that if you have perturbation or something, then you have precession. You don't have precession if you solve just this problem, okay? But from the point of view of general relativity, it's due to the fact that this is not the real potential. There are corrections, and those corrections produce precession. So you see, for Newton, it was just a coincidence. For Einstein, it was the clue for the theory of general relativity. So, one has to be careful before throwing away things. Okay, so that's what I wanted to say. Well, maybe I spent too much time on this idea of solving problems. But you see, it's very effective, very nice. We reduce the problem to a one-dimensional system with this effective potential, and then we are able to almost, we know the solution. I mean, now it's only a matter of working out the details. But of course, the details are important in physics. So let's write the equation of motion now. We have the Lagrangian. Let me erase this effective potential. Well, we only need the Lagrangian. That's all we need. So, well, I mean, there are many ways to do this. I mean, there are many ways to skin a cat, they say. But let's just write just to show that. Let's. First, I write the. So one equation of motion. We already know it, right? If I take the theta is conserved, right? The theta dot is conserved. So one equation of motion, it's kind of trivial. Let's look at the one we haven't looked yet, because we have been fooling around with the effective potential. So now I take the partial derivative of the Lagrangian with respect to the other coordinate, that is r. There is where all the dynamics is. And again, I can do that just by inspection. Partial derivative with respect to the velocity, so it's this one. So I get my mr dot, and of course, I immediately dot it again because of the derivative with respect to time. So this is the acceleration. Then I have the minus the partial derivative, right, of the Lagrangian with respect to r, the coordinate. So I have to take a partial derivative of the. So this is minus m, right? The 2 kills the 2, theta dot square, okay? And this is minus dv dr, because remember, the Lagrangian is not only the kinetic energy, it's also the potential. So I have, so this if you, and if I use my second equation, that is just the conservation of the angular momentum, I can always rewrite this as L square, as I said, mr cube now. So one can try and solve this directly. In fact, one way is, now probably I haven't told you that, what we, so really you can solve this problem in two ways, right? You can write r as a function of theta, or you can write r and theta as a function of time, right? Usually, you see, these are called the trajectories. That's what I've been talking about all the time. We solved the problem, we found the trajectories, that is the change in time of our generalized coordinates. But for this kind of two-dimensional problem, a very effective way is to write so these are trajectories. This is called the orbit. I've written one coordinate in terms of the other, and you understand why it's called the orbit. These are trajectory in time, so I give you, so this is the orbit. So you see, this is r theta, r and some theta, I don't know, I start measuring from here. So either I give you r of theta, that is this orbit, or for each point I give you r and theta. So there are two different constants, no? Then you bring them together. But the solution, so in this business, very often you give the solution in terms of the orbit, as I did here. But in general, you give the trajectory. So if I were to solve this equation, you see, by integrating that, I would get r as a function of t. Then, through the conservation law and a further integration, I would get theta as a function of t, so the trajectory. But I can also switch around, exactly because I have this, you see, because I have that L is equal mr squared theta dot, right? That means I have that L dt is equal mr squared d theta. Now, a mathematician will just faint here and leave the room, because you see what I'm doing. I just write d theta dt. Then I forget that this is the derivative. I take this piece, I put it there, and I leave it there. That's complete nonsense. So maybe we cut this from the movie, but it works, right? I mean, that's the beauty of Leibniz notation. I mean, he wrote it like this, and this works like. Of course, it's not correct. You understand? This is a derivative. It's not a small theta over a small t. Mathematicians spend most part of the 19th century to explain what this is, but we physicists, we don't care, and we do that. They will never stop us until we are dead. Anyway, but now you see what I can do. I can trade the dependence on t with the one on theta. So I can transform this equation that originally would have given me only r of t in the equation of the orbit. So because of this relation between theta and time, due to the conservation of the angular momentum, I can always switch using the same equation roughly, and instead of studying the trajectory, study the orbit directly. So I want to just go and do that if I have time. Did you understand what I'm doing, or it's complete, I'm out of my mind? Do you feel the same need of doing that, or it's just, you see, you understand this? These are two different ways of giving you the solution. Is where I started. I say you can describe this motion as a geometrical object that is this is the orbit, or you can tell me at each instant in time the coordinates. There are two, right? Now, in the business of the motion of planets, usually, as you know, people talk about orbits. So orbit means that I give you the position r as a function of the angle. So I draw a curve, right? You know this curve for a circle is such, right? For a, I don't know, the hyperbole is a different one. We study all those curves. But that's what I want to do. So I don't want to solve r of t and then theta of t and then this system solve it together to get the orbit. I see that because of this relation, I can trade this equation that is a differential equation with respect to time. I can trade derivative with respect to time with derivative with respect to theta. So then I get the solution. It's directly the orbit. Okay? Do you want to do that? So let's do it. Was there a question? Yeah, sorry. You should stop me. What? No, this is equal to this. It's not that it's multiplied. I just rewrote explicitly, because this is Newton notation. Then I was carried away to tell you how beautiful is Leibniz notation. You know that these things were invented by two people at the same time. One was a German Leibniz guy, and the other was Newton. And they argued for a long time who was first, and okay, it doesn't matter. But the fact is that Newton's notation is nice because it's very compact, but Leibniz notation is more suggestive, and it even helps you in doing this trick. So, okay. So you see that I can if I look at this now, I take the, so look at d dt, for me is, you see, I take L, so let's do this. I take it 1 over dt, yeah, I call it 1 over dt is equal to this, and I take it on the other side. So I have L m r square d dt theta. That's what I wanted to say. This way, I trade a derivative with respect to time to a derivative with respect to theta, and so I can plug that in here. The only thing I need is, this is the first derivative, so what is the second derivative, okay? So first I replace by using the conservation of the angular momentum, this with what I wrote downstairs, okay? And then I replace this, so I have m L m r square, right? d theta, but it's the second derivative, so I have again d dt, that again I write like m r square d theta, okay? And here I have r. So this is the second derivative with respect to time, rewritten in a new notation that is a second derivative. But you see, it's a little more complicated because r depends on theta, obviously. So when this goes inside, you have to take care of this term. Then this is fine the way it is, and also this is just whatever it is. So this is my equation for the orbit now. So this was the equation for the trajectory. The one boxed is the equation for the orbit. And now I can forget, and I erased this before I'm arrested. And you see, everywhere there is 1 over r, so usually in this business, people call, they introduce a new variable that they call u, that is just 1 over r, okay? And then you should only be careful that du, right, du is minus 1 over r square, dr. And if you do that, the equation sort of simplify, because you have, you see, 1 over r, so you have to replace everywhere r with 1 over u, sorry, 1 over r with u, and also dr is replaced by du, okay? So what you get is minus L square divided by m. This, I'm writing this term here. I get an extra L, u square d theta du d theta. You see, the nice thing about this transformation, I mean, is you see that dr, you see dr over r is just minus du. So you see, that's why this transformation is nice. And then I have this term here that obviously is just minus L square over m, and then I have 1 over r cubed, so I just have u to the cube. And v, that is a function of r, becomes just a function of u, okay? Okay, so this is the way, this is the equation that you, well, you can, this is the form you usually, sometimes it's written, you can, you see, you can simplify u and bring it there. So you have a nice form for this equation. The second derivative of u with respect to theta square plus, so you multiply ml square, you bring it on the other side. So plus u is equal minus ml square. Now you get this extra 1 over u square, but you see it's in this form. So this is okay if the v of 1 over u. So this is still, now I have this that looks nice. It's the second derivative plus the function itself is equal to whatever this derivative is that I cannot do because I don't know how v depends on r. It will depend. For the Kepler problem, it's going to be minus k u. For a harmonical oscillator, it's going to be something different. But it's a second order differential equation. And also, you see something that maybe was not completely obvious here. This equation is invariant for the exchange of theta into minus theta, right? Because it only depends on the second derivative of u with respect to theta. So if I change theta into minus theta, nothing is going to happen. So that means that you can all these orbits all the orbits that I'm going to find solving this equation are going to be symmetric with respect to a reflection. In other words, if I give you half of an orbit, you know already how the other half is. And this is essentially, even if it's like this, right, this is half. If the comet comes this way, then you already know the way it's going to fly away because you just do, it's like in a mirror, right? It's a mirror transformation. And the same if it's a closed orbit, obviously for a circle, for an ellipsis, and so on and so forth. In fact, all the orbits we will find are going to satisfy this principle. And this is already there in this form of the equation. Okay, so orbits are symmetric about turning points. These are the turning points. This and infinity and so on. So this is a possibility if you, I mean, this is not a very simple differential equation. I mean, this part, if there is zero potential, this you recognize. What is the solution of this differential equation? Right, it's just a trigonometric function. But unfortunately, you have some piece here that you don't know, and in general, it's not going to be that simple. On the other hand, I can look for the trajectories, right? So let me do that, and then we stop. So this is a way. I look for the orbit directly if I'm clever enough, or if I have Mathematica, this nice program that integrates everything. I can plug in my differential equation and find the solutions, okay? And that's what we are going to do on Friday. So this was the orbit. I can also pursue the other idea that I want to look for the trajectories. How I'm going to do about that? Well, there it's more effective to use the other trick. That, remember, is that rather than having to deal with second order differential equations, I'm happier if I have just first order differential equation, right? It looks like less work. So how can I use first order differential equations? Well, I go back to my conservation laws. You know that the conservation laws are first integrals of the motion, and that means they imply the velocity rather than the acceleration. So if I write my two conserved quantity that we have already written, so the energy, m divided by 2 r dot square plus r square theta dot square plus the potential. So I'm back, and this E is a constant, right? And then I use the other one that is just mr square, right? Again, it's just, so this term here, just, well, I can rewrite this like 1/2 mr square plus 1/2 L square mr square plus the potential. Okay, and this is still the energy. So I've used, as before, one of the conserved quantity to get rid of theta dot, and then I'm left with a differential equation now that is just this. And as before, for the potential, I only have the velocity, so this I, in principle, know how to integrate. Okay, so this is one, and the other one is just so these are the equations. And if I solve them, presumably I found r of t and theta of t. That is what I call the trajectories. So that's the other side of the coin. And you see that I can write the solution, right? Because it's rather simple. It's just it's a total derivative of r. So I can bring everything on the other side and write r dot is equal to what? Well, I take everything on the side of the energy. Is what I did before for the potential, right? 2m E minus the potential really is the effective potential, because I also have, now I keep it explicitly, this funny term that comes from the, I guess there is a square, that comes from the, and you see that this I can integrate, right? If you tell me what this function is, then t, because this is the, let's switch to, so again, I take dt here, I take this on the other side, and I do the integral, so I have t is equal to what? Initial condition, so the position at time t equal to, I don't know, 0, to the position at which I'm computing the orbit of this integral, dr, the square root of whatever is here, so 2m e minus vr minus this angular momentum. So presumably, if Vr is a simple enough function, this is the integral that I know, that I can find in that book I suggest you get hold of, or through Mathematica, and then you see this is, the solution of this is t as a function of r, the energy, and L, and the initial position, right? That's the solution, that's the trajectory. And when I, well, actually a trajectory, I have to, once I know this, I just invert this and I get r of t, right? So you invert and you get r of t and r0, and of course the energy and the angular momentum. And once I know that, I can integrate this, you see, because this is rather simple to integrate as well, because I do the same trick, and you see that theta of t is the integral from time t, initial time that I can always pick to be 0, to the time t at which I'm L dt of mr square of t plus some initial condition. I should have, here is t0, but this I put it to 0. So you see, once I have r of t, the trajectory, I put it here, and I do this integral, I get theta of t, and I've completely solved the problem. So this is theta of t and the initial angle, given the energy and the L, given the energy and the angular momentum. Okay? from this expression, anyway, I can always go back to the orbit, you understand, right? Because at this stage here, so let me write it here, when I write dt, so let me eliminate the integral and write dt. dt, I said, is dr square root of e minus vr minus L square to mr square, right? But again, I can always use the trick I use for the equation to get from this the equation of the orbit, because remember, d theta is L dt mr square, right? So you see that from here I can trade dt for d theta and get L dr mr square, the square root, the same thing that is up there. So again, I can go to the other and solve this and the solution of this is going to be the orbit. So let's do that, and then I stop for real. So if I integrate this, I get theta, right, as a function of r now. So now we are talking about orbits again. Actually, I like the orbits better than the trajectory in this case. As you see, it's the integral from the initial position to r of dr, right? Then let me take m inside, because you see that I get rid of these m's here. So I have r square outside. That's OK. And then I have the square root of what? 2me. So I take L and m inside. So I have a L square down, right? Then 2mv, the potential, divided by S square. And then I have, right. So I'm already simplifying a little bit. And now again, remember the substitution that I did for the differential equation. You see, you have dr over r squared. So if I introduce u, this integral, now I change variables to simplify the integral. So, okay, here there is a theta naught, because, right, so you have theta naught minus now the u naught u. This is the u, so u naught is the 1 over r naught. I mean, it's obvious. And now I have du. This minus du takes care of this dr over r square. And then I only need to rewrite, well, 2me over L square is just a constant, so I don't have to be clever. And also this, I mean, 2mv, that is a function of u now. And here you just have 1 over r squared, that by definition is u squared. So again, if I solve, this is u as a function, theta as a function of r, or theta as a function of u in this case. So you see that if the potential, now I have to, I mean, that's as far as I can go without telling you what v of r is clearly. Where? Why? No, why? Because du is minus dr r squared. So this is du. And then I simply replace. Yeah, but where is 2? 2, no, 2me. 2 this? No, because so
over 2m r squared.
You wanted 2 here?
Yeah, there also different.
Okay, I'll check it. But it shouldn't be there, so I made a mistake somewhere. I think
We will correct it. We will.
you will. Okay, I will too. Okay, but let me just keep it this form. That I only wanted to add, now I have to say something about the potential. In general, this is a central force. So I can think of the potential as, say, some constant, okay, then R, and then I can think that, okay, it can be any function, obviously. It can be the sine of R, the exponential e to the minus R over R0. But let's just consider potential that go like powers of some exponent, right? So in this form here, where n can vary. And what I wanted to say, you see that if I plug this in here, okay, in here, I have 2me L square minus 2ma L square, that is just a constant. And here you have u to the minus n minus 1 minus u squared, maybe with a factor of 1/2, it doesn't matter. So you see that you have an integral that you should be able to, you see, it's an integral in the form dx square root of a x squared plus bx plus c, right? If you take my meaning. You have an integral that is 1 over the square root of a quadratic polynomial in U. I'm sorry, not a quadratic polynomial. Yeah, here you have the powers, right? Minus n minus 1. So depending on what n you take, here you have a quadratic, a cubic, whatever polynomial. What I wanted to say is that you can check on this table of integrals. You know, these integrals, as I said, they are all classified in that book, and you can find all the possible polynomial there. But the fact is that if n, so now the homework can go. If n is equal to 1 minus 2 minus 3, so that means potential that goes like r squared. What is that potential? A potential that goes like r square. It's the harmonical oscillator, right? Because it's a force that is proportional to the distance. N minus 2, so minus 2 plus 1 minus 1, that's Kepler problem. And also minus 3 plus 1, so 1 over r squared, so a sort of super Kepler. Then this integral can be written in terms of trigonometric functions. So the solution of this problem is going to be some combination of this trigonometric function. So That's highly non-trivial. So we know the solution of this problem exactly, and it can be written in terms of elementary functions, trigonometric function, for this case. If n is 5, 3, 0, -4, -5, -7, again, I know the solution. For other values, I don't know the solution, but for these values, I know the solution. But the solution is a little more complicated, but can be written in terms, you remember these elliptic functions that I mentioned with regard to the pendulum. So these are functions that can be written as a you study the hypergeometric function, so you know that if you know the hypergeometric function, you know all these special functions because by choosing the coefficients of the hypergeometric function, you can describe most of the other special functions. So in these cases, so these are potential, I don't know, this is, you see, 5, it's a potential that grows like r to the 6th, whatever. I know the solution is an elliptic function. That means this integral becomes an elliptic integral, the same that I had in the case of the pendulum, when the oscillation is not that simple. But at least for these three cases, and in particular for these two that are the most relevant for us, not only I know the solution, but the solution can be written in terms of elementary functions, meaning functions that you have already met, and that's what we are going to do on Friday, to write this orbit in terms of these elementary functions. Okay?